show this has been very common so far. Good job. Even this morning, blocking with the device, I would have gone nuts. No, that was well handled. Okay, so prefractal is basically just a fancy word for the approximation of a particular fractal. Who knows what the Koch snowflake is or a Sierpinski carpet is? Who does not? Okay, so I'll spend a little bit of time, a little extra time talking about those just so you have an intuition for what those are and why they make very unfriendly billiard tables and why they will hopefully give rise to translation surfaces that will be equally unfriendly. So this is in collaboration with my PhD advisor, Michelle Atticus. In particular, work on the Koch snowflake and some stuff on the T-fractal billiard. And stuff that we've done on the Sierpinski carpet has been done with Joe Chen, who just graduated from Cornell, now at UConn as a postdoc, working with Sasha Paplaya. And then some new stuff done on the T-fractal billiard is in collaboration with Michelle and now Ron Miller, who's actually defending in 3 or 4 days at Cornell. And hopefully that defense goes well. I'm sure it will. David, you did a great job on the background stuff from yesterday, so I'm going to go over this a lot quicker than I would have otherwise. The billiard table, the notation that I'm using is omega of D, where D is the boundary of the table. The rational billiard table, like David said yesterday, is one for which the interior angles are rational multiples of pi. Examples of rational billiard tables. Here we have the equilateral triangle, the square, and this, perhaps not a conventional example, this T shape right here. And you notice we start at this red dot, and we go off at that particular angle, and we hit these right angles right here. The reason why we can say that this billiard trajectory makes sense when you're hitting those corners is because they will constitute removable singularities in the associated translation surface. So, I actually recently learned that Eugene has passed away, which kind of felt a little sad about. He had a result in a paper, I think it was 1982 or 1984. I always get those mixed up. I know it's 1 year plus or minus my birth year. Fixative correction on the billiard table, the flow is either going to be closed or minimal, regardless of where you started from. In particular, the more general result says if you have an almost integrable billiard table that's tiled by an integrable billiard, then the direction, the flow in the fixed direction is either closed or minimal in that billiard table. And the reason why I reduce this to equilateral triangle or square is because the 3 fractals I'm talking about, their prefractal approximations are tiled by either equilateral triangles or squares. So let's try to put it in context. So let's skip this and just give examples since David covered that yesterday. So if we take the equilateral triangle and we make sufficient number of copies of it and identify opposite and parallel sides, we can get a translation surface. Here's the billiard table, there are the corners, and the singularities are identified as such. All the yellow are exactly the same singularity, blue are the same singularity, and the red is obviously the same singularity. Now these are all removable, and that's a nice thing. The square, we also get a torus again. There are the singularities, they're all removable, we're happy. Now this T, however, if we were to take 4 copies of the T and identify sides according to these colors, then we have non-removable singularities right there, but we have removable singularities at the right angles. So just some basic facts. The billiard table can be enfolded in the associated translation surface.
Excuse me, sir, what is the surface associated, the last one, billiard? This one, what is the surface?
What is the surface?
Yes.
What do you mean by what is the surface?
So when you build the parallels in the sides.
Okay. So here's the identification right here.
Yeah, yeah.
So this segment right here is identified with this little segment up here. This is identified with this. Usually we see like A, B, C, D, or 1, 2, 3, 4 Roman numerals, but as you can imagine, if I'm going to start generating a fractal, even the number of colors we have isn't enough to actually make the identification. Well, depending on what you mean by colors. But yeah.
It's a
Does
continuum.
that make sense though? Does that clear up your
So what's the genus of that surface?
bigger than one? There is that formula in Boston-Cobb and Mazur's survey paper that can be used. I think it's
Probably 3.
3, I think.
Come on, people, let's do that. We can.
What's that?
It's probably 2 or 3.
Three.
It looks like a torus to which you glue 2 other tori.
Yeah.
Okay. Okay.
Yeah.
We'll talk about that later. So here are the singularities, corners, and then the corresponding points in the translation surface. Okay, so what happens when the billiard flow, what happens to the billiard flow when the boundary is non-differentiable? In particular, when we're dealing with a boundary that is fractal in some sense, or at least some subset of the boundary of the billiard table is fractal. So the 3 fractals I'm going to focus on are the Koch snowflake, the T-fractal, and a self-similar Sierpinski carpet. And I say a self-similar because depending on the scaling ratio, you can get a different carpet. And a little detail here is that A is actually a bold-faced A because it's really a sequence of rational values. And I'll discuss that a little bit more later. You might be interested in that. There we go. At least Joe Chen had said you might be interested in that. So the Koch snowflake, denoted by KS, is constructed as follows. Start with an equilateral triangle, and off each successive side, a equilateral triangle of scale 1/3, or 1/9, etc., etc., 1/3 to the n being the approximation. And then in the limit, you get something that has something that does not have a well-defined tangent at any point. So a lot of reflection isn't going to hold at any point. So how do you actually do billiards on a table where your boundary is that? Here is the T-fractal. You remove the segment right here all the way to that point and then append a scaled copy of the original T and continue ad infinitum until you have at the top what would be a self-similar Cantor set. Move that mouse. You never quite get rid of it.
The answer is not here.
Now this is supposed to show you the construction of a self-similar Sierpinski carpet, but for some reason decided not to work this morning, even though it did last night. So that you have an idea of what this is and why it's called self-similar. So you start with a unit square, and then you remove. So if this is unit length, this would be 1/A. This side is 1/A. Where A is some odd number greater than 1. So 3, 5, 7, 9, etc., etc. And then really what you're doing is you're dividing this up into cells. And from each cell, you remove then something of side length 1/A squared. And you can tell this is supposed to be something where A is in fact equal to 3. And we could have A equal to 5, A equal to 7, and really you could have 1/3, 1/5, 1/2k plus 1. This also be some sequence of rational values where at each stage you're partitioning and scaling differently. And in that case, you get a self-similar carpet if you have a periodic sequence of rationals, or it's a non-self-similar if it's an aperiodic sequence of rationals. Yes.
So it looks like the wind tree, but in a nutshell.
Yes, yes. Actually, a referee of a paper has suggested I look at the wind tree model for inspiration on how to deal with the billiard table and also perhaps whatever should be the associated translation surface. So this has been very, very helpful. So we're primarily interested in self-similar Sierpinski carpets. And like I just said, we could have a sequence, but really here, if we were to show the sequence, it'd be 1/3, 1/3, 1/3, dot, dot, dot. Yeah.
Is there a particular reason when you have odd numbers?
Yes. I could think of the answer if not on the spot. But yeah, it basically has to do with the fact that you want to be able to remove a middle square, right? So if you have, let's say, 1/2, well then you can't really remove a middle square. 1/4. You're thinking maybe of a Sierpinski carpet, where suppose you had 1/4 as the side length you're removing, but then this, yeah. I think I know why you're asking. We'll talk about that later. But yeah, basically you want to be able to remove a middle square.
Do you want all your boundary components to be like squares?
What's that?
Do you want all your boundary components to be squares?
I want my boundary to be square. So
All your boundary components.
something with the echo.
Well, if you have a square, you sort of divide it into 4 and remove a corner, then you've got an L-shaped thing. Right?
Yes.
Yes, you don't want here.
No, I think, let me draw something.
When it's odd, you have a central square. And that's what you want.
So it's even, then you get L-shaped, right?
Right.
So if I was to remove something of, side length, let's say 1/2, then it may be self-affine and not self-similar. Self-similarity, so the reason why we're taking, another reason why we're using 1/2k + 1, where k is an integer, is because we want to get something that's self-similar. And I want to say that this may not be self-similar, it may be self-affine. Yeah. I'll see if I can come up with a better answer for you later. Short answer is just because we always do. And again, this GIF or GIF is supposed to move and do things, but it's not. The other ones are actually flash animations. So the benefit that we can, or the thing we can take advantage of it is the fact that each prefractal approximation is tiled by an equilateral triangle or a square. So some notation that I want to introduce is this right here, E sub f. The set is called the set of elusive points of a fractal. And this is sort of non-standard terminology, but it's useful when trying to understand what might constitute dynamics on a fractal billiard table, because if you're looking at a sequence of approximations and orbits on them, there are certain points that a trajectory won't reach in a finite approximation that exist in the limit when you're constructing the fractal. In the case of a self-similar Sierpinski carpet, E sub S of A is in fact empty. So right here should be, so here is a point right there on that side. When we construct the Koch snowflake, that point right there is going to be in the interior of the next level approximation. So if we were to find some way to continue going out and identify some point in the boundary of the actual fractal billiard table, that's going to be called an elusive point. And it'd be right somewhere right around there, maybe, as an example. This is a corner. This is what we call a canter point. So think of 1/4. 1/4 in the unit interval is something with a binary representation of 0, 2, 0, 2, dot, dot, dot. 1/4 is approximately right there. It always has an open and connected neighborhood around it. So the law of reflection holds at the point right here, for instance, in every subsequent approximation. So if you have a trajectory coming in at that point, coming in like this, and hitting that point, and every approximation is going to bounce off the same way. Now what it does after it bounces, who knows, but in each approximation, the trajectory coming in leaves according to the law of reflection. So I'm going to skip the addressing system. It's not so important, but there is one for the snowflake. And then here are what we just call corners of a Sierpinski carpet. They're just corners that were corners of some finite approximation. And again, there's no elusive points because remember that the definition says it's the fractal minus the union of the approximations. Well, the union of all the approximations is going to be contained in the fractal, so there's no elusive points. So here's the T-fractal. That's a corner of the T-fractal. And then up here are the elusive points. The points that never exist in any finite approximation. These are the points in the T-fractal that are giving us the trouble when trying to determine periodic orbits of this particular fractal billiard table. And that's primarily what I focus on. Even though we have a dichotomy for what we call sequences of compatible orbits, I'm primarily focusing on periodic and closed orbits in the stock. So points of the E sub t constitute a self-similar Cantor set and can be addressed using an alphabet given by L's and R's. So left, right. Now if we go left, then we have a choice of left to right, left to right. So up here is something with a periodic address, and we call that a rational point of this Cantor set. And then over here is something with an irrational, or we call an irrational point, because it has an aperiodic address in terms of L's and R's. Is that clear to everybody? Some notation. Let Fn be a prefractal is approximating to Ks, Sa, T, and I'll at times refer to these as the fractals of interest. So an orbit of an nth approximation with an initial base point and an initial angle, which I might take to be a slope sometimes. I'll switch back and forth between slope and angle, depending on what table I'm dealing with. So we want to have a way of making sense of orbits of prefractal billiards. So that way in which we make sense of them is called compatibility. Now this is just a fancy way of saying that the base points are all collinear in the same direction. So as an example, I'll show you a sequence of compatible initial conditions for, or when prefractal billiards approximate the Koch snowflake. So that little orange dot is where we're starting, and we're going in some direction. In the next approximation, that point we started at is now in the interior of that approximation. But this point right here, x10, is collinear with that point if we go in the same direction. Well, x10 is x20 in the next approximation, but in the third approximation, x30 is right there. If we go in the same direction, we intersect x10, which is x20, and we would also then consequently intersect x00. So a sequence of compatible initial conditions is just a sequence of initial conditions where they're all compatible. And a sequence of compatible orbits is just a sequence of orbits where the corresponding sequence of initial conditions is a sequence of compatible initial conditions. Is that clear to everybody?
So when you say collinear in this case, you mean collinear in the direction of the angle you picked.
Right.
Okay.
Fixing an angle and saying, okay, another way to think about it is if you're this billiard ball and you're going in that direction, well, suddenly where you're standing no longer is a point of boundary. You want to still go in the same direction, so you just drop back to when you next hit the boundary. So building on that result of Eugene Gukin, we have a sequence of, if we can consider a sequence of prefractal approximations by the Koch snowflake, A so similar to this covered with the T, then a sequence of compatible orbits is either a sequence of compatible closed orbits or a sequence of compatible dense orbits. Ultimately, what I would like to have is a topological dichotomy for the billiard flow on a fractal billiard table. We're quite a ways away from that, but this is at least a nice step in a direction that I want to go in. So an example of a sequence of compatible periodic orbits, starting here at the midpoint, going in the direction of pi over 3, we get this orbit. This is the orbit that's compatible with that orbit. This orbit is compatible with this one, which is compatible with that one, and we can form a sequence of compatible orbits of prefractal billiard tables. And more importantly, this sequence we get never contains any orbits that are singular in their respective approximations. So that's why we say it's a sequence of compatible periodic orbits and not just closed. And an additional example of a sequence of compatible orbits, starting here at 3/4 and going in the direction of pi over 6. We don't really have anything that looks like an orbit because this is in fact degenerate. That's a right angle right there where the billiard ball meets that side, so it bounces off and then comes back. And in fact, both ends of this orbit are forming logarithmic spirals. Something a lot more convoluted, and this is when it starts to not be very pretty. Well, if we start here at the midpoint and go to this point, which would be the midpoint of this side, we get this sequence of compatible periodic orbits. Still a sequence of compatible periodic orbits, but yeah, I'll say more about that later.
So in the previous two examples, the sequence converges to something of finite length, but these lengths are going to infinity, right?
Right, this will converge to something of finite length. This will certainly converge to something of finite length. I don't know if this is going to converge to something of finite length or not. I hope it does, but there's something called a non-trivial path that does converge to finite length and serves as a model for what should constitute a periodic orbit of a fractal billiard table. And in the snowflake, it's less clear what we do once we hit an elusive point, but it's very clear what we do in a T-fractal. So yeah, you're right that this may not converge, but we do see something that does converge, basically, in a sense, a subset of this orbit. So there's at least countably infinite many initial base points and initial angles such that the sequence of compatible orbits is a sequence of compatible periodic orbits. So starting from at least countably infinite many base points and angles, we can get sequences of orbits that contain orbits that are never singular in their respective approximations. Now this might seem nice, but really all it says is, hey, you can get a sequence of orbits that's not going to hit any corners in finite approximations. What we would like to say eventually is that the same, now I don't list the actual points and angles just because I don't want to convolute the slide, but when I introduce something called a non-trivial path, it would be nice if the points and angles that we have actually give us non-trivial paths. And you'll understand what that means in a few slides. So here's an example then of a sequence of compatible periodic orbits of the T-fractal. Starting there at 1/3, going the direction such that the slope is 1/9, we have this sequence of compatible periodic orbits. And you can clearly see that this sequence of compatible orbits is in fact converging to something. And this is just one example of a larger family of sequences of compatible orbits that do exactly this. So let me, how am I in time? When did we start? 11? Okay. Let me skip the slide and then say, okay, the work with Joe Chen, we have a sequence of compatible periodic orbits. So starting here at this corner right here, we have orbit of the square. And you would think we're going to hit some square that gets removed in some finite approximation, but in fact, we don't. So beginning from the origin 0, 0, there are finitely many appropriate initial directions for which a sequence of compatible periodic orbits results. And then starting from the midpoint, there's a different collection of slopes that we can have, such that the same thing happens. But it's particularly important that when you start at this corner right here, that you pick a slope from a particular set. If you pick the slope from a different set, you won't get a sequence of compatible periodic orbits. You'll in fact get a sequence of orbits that converges to exactly this point right here. All right, so towards a fractal billiard table. In a fractal billiard table, or in each fractal billiard table, we can determine interesting dynamical behavior. So we've seen sequences of compatible orbits that appear to be converging to something. We've seen sequences of orbits that don't appear to be converging to something. But what we can find are sequences of compatible orbits that are constant after a certain point. And then what I mentioned before, a non-trivial path of a billiard table. And so right now we're going to talk about constant sequences, and then we'll talk about non-trivial paths, and then we'll talk about the translation surfaces. And if time, I'll probably mention a couple of things that I talked to Anya about yesterday. There might be an alternate approach to determining a fractal translation surface, independent of whether or not you started with a billiard table. So thus far, with regards to the Koch snowflake, we have only two directions for which we can get a sequence of compatible orbits that's eventually constant. So starting here, you have this orbit, and that point does get removed from the boundary, and here is the compatible orbit, but from here on, we're constant. So this is a constant, so from this approximation on, we have a constant sequence of compatible orbits. So same thing with the carpet. Starting here at the midpoint now, we have this direction, and this orbit will now hit that square, but this orbit does not hit any other squares in any subsequent approximation. Another example of a sequence of constant orbits. we see here an orbit of the square. Well, here now it hits the square that gets removed from the first approximation, but does not change from then after. An example of a sequence of compatible orbits with eventually constant. Well, here I show multiple orbits in the same approximation. And the reason for this is because this orbit right here doesn't change from one approximation to the next. Neither does this orbit in this approximation, but what you can probably notice is if I scale this orbit, I can move it anywhere I want in that approximation. So this is why we say that the T-fractal is a lot easier to deal with. There's a lot more results. There's a lot more interesting results. And this is the table that I'm starting to focus on more to, one, gain inspiration for how to deal with a snowflake, even though that's what I originally started with. And two, it's a lot easier to deal with. So a non-trivial path is a path in the billiard table reaching a point on the boundary that is never any point of any finite approximation, in particular, an elusive point. So such a path is determined using law of reflection in successive approximations. So going back to the hook orbit, starting at 3/4, going in the direction of 5 or 6, we form this path that's constructed by reflecting off of points that are Cantor points of successive approximations. And we can converge to an elusive point in the limit. And here's an additional example. Before I showed you that sequence of compatible orbits that was not very pretty, didn't seem to converge into anything. Well, this is what's converging. Starting here at 1/2, going to the point that would be 1/6 on that side if we're looking at an approximation. We can zoom in more and more and more. And more importantly, we can actually just throw away the law of reflection in this, constructing this non-trivial path, because we recognize that this shape right here can just be scaled by 1/9 and appended to a certain point. So we forego the law of reflection altogether when constructing this non-trivial path right here. And we can do that in a number of cases. We have a number of examples for which that is true. So a non-trivial path then in T-fractal is constructed like this. Starting from 1/3, slope 1/9, we get this path. And just like we saw in the previous image with the snowflake, there comes a point where we can just say, okay, well, we're hitting a particular point in some approximation. We can copy that part of the non-trivial path, scale it, and append it, and just keep building up and up until we reach the elusive point. We can forego the use of the law of reflection when constructing this non-trivial path of the fractal billiard table. So the set, or this particular fractal T, contains, as I mentioned before, a topological Cantor set. And the notation isn't so important, but as the result is one result. So if we consider a sequence of compatible periodic compatible periodic orbits, yielding some non-trivial path like we saw in this figure right here. So some sequence of orbits for which we can get this non-trivial path. Is everybody clear on exactly how we would do that? The ambiguity as to how we construct that non-trivial path from a sequence of orbits. Fantastic. Good. So constructing one of those, if we start at something like, say, 1/3, some rational value, we will converge to a rational point of that Cantor set at the top. And if we start at something, say, 1/2, we will converge to an irrational point of that Cantor set. Originally thought that a sequence of compatible dense orbits would yield a non-trivial path that would converge to an irrational point of the Cantor set, but that's not the case. What's going on with a sequence of compatible dense orbits is still wide open, but we think we might have a way of taking the limit of a particular sequence of compatible dense orbits such that it's dense in the T-fractal and not the whole T-fractal. So we're still working on that, but that's the direction we want to go in with respect to that. So, here we have a blue dot. Why blue? Well, I want to just visually convey the fact that now we're looking at two non-trivial paths. Going in the direction of 5 or 6, we can get this non-trivial path. Going in the direction of 5 or 6, we get this non-trivial path. Well, this is utilizing, in effect, the law of reflection, some approximation. So this is a way of connecting that elusive point with this one right here. Same thing for the T-fractal. In fact, before, we saw this sequence of compatible orbits getting tighter and tighter and converging to something. Well, it's in fact converging to these two non-trivial paths. So what this is telling us is that if we have a sequence of compatible orbits, what do we do once we reach the elusive points? Well, we can just come back out the same path we took to get there. Yeah.
So, maybe you could say something about this. Is it possible to just pick any two elusive points and find a path that connects them, or are there conditions on those points so you could connect them?
There might be conditions because certain points in that Cantor set at the top have, there's two, so given a point, there may be two addresses for it that would then indicate that there's two different ways to approach it and perhaps two different non-trivial paths that would tell you how to get there. So if you stipulate in a direction and then try to construct the sequence of compatible orbits that converges to it, that might be how you want to say that if you start there, how do you depart from there? We're still working on that detail, but this is saying if you reach there, how do you come back? All right, so when did we start? It was 11, right?
Right.
Okay, excellent. So towards a fractal translation surface, suppose we focus on fractals of interest. And if we have a sequence of prefractal billiards, we want to try to see what's happening geometrically and also algebraically with the sequences of translation surfaces, where SFN is corresponding to omega of Fn. So here is 6 copies of our prefractal billiard table. We have 6 because of the nature of the interior angles, and we have 6 copies of our approximation every subsequent translation surface. So this side right here is identified with that. This side right here, up here, would be identified here. This side right there would be identified with this side right here. And as you can imagine, trying to label these becomes quite tedious. Sierpinski carpet, this side right here is identified with this side right here. That right side is identified with this left side right here, and so forth. And then the T-fractal, here's a second level approximation, and third level approximation of the translation surface. And what we want is for these sequences of translation surfaces to converge to something that ends up being a translation surface in the limit. How it is we do that, we don't know yet. As you can imagine, you get more and more singularities, so it becomes increasingly difficult to determine what happens at certain points. So translation surfaces, okay, so translation surfaces determined from an equilateral triangle, a square of both tori. This is, this billiard table is still tiled by squared, so there's a lot of things to take advantage of in trying to determine what might constitute the geodesic flow on the associated translation surface. But the number of saddle connections increases with n. I mean, granted, it's countable, but they become, the singularities are going to become dense in the boundary of the billiard table, and consequently make lots of problems for the geodesic flow on some associated translation surface if we can even construct that. So here is a periodic cylinder on the torus, and here is the saddle connection that we were to start right here. So this is also a geodesic on this surface, so we start here and go there, and we'll continue around and form a closed geodesic. But if we iterate the surface, we're starting from that same point right here. So suppose, yeah, we start right here. Suppose we start right there. Well, here is the point right there that we would have started in the equilateral triangle. Well, there's the compatible point right there. And this is now the periodic cylinder. And in fact, what we see with the sequence approximations is these periodic cylinders, in a sense, being continually broken up and feathering in a sense. So here's that same geodesic that we saw before, right here in this, right here in the sense the compatible geodesic would be right here in that cylinder. And then in the next approximation, this is what the geodesic looks like on that surface. And then here's what the geodesic looks like on that surface. So not only do we not see a very nice convergence at all in the sequence of compatible orbits and billiard tables, we're not seeing anything very nice in the sequence of compatible geodesics, if you will, in the corresponding sequence of translation surfaces. So here is everything superimposed, which is, in a sense, completely useless. And you can say, you look at that and it's not at all useful. And that really kind of starts to indicate to me that trying to look at sequences of things is probably not the best approach, at least for the snowflake. A similar situation for the T. So we're going to look at 4 copies of the T, appropriately glued together. Here's a periodic cylinder. Maybe you can see the gray is not so clear. So there's supposed to be a slightly lighter line right there. And in the next approximation, this is the cylinder. The black is now a cylinder, as well as the white that's in between the black. That's a different cylinder. So it's being divided up in the subsequent approximations. With each subsequent approximation, we're getting smaller and smaller, thinner and thinner cylinders. And here is a geodesic that would have started at point 3 and remained in this cylinder, started at point 3 and remained in this cylinder, black. And then if we superimpose the two surfaces, it's a little nicer to look at. There's a little bit more useful information here compared to the snowflake. Now starting at point 6, we get this sequence of, or we get this geodesic and then this compatible geodesic right here. And if we superimpose the two, we see that there's some useful information here. In between, we can see the parts of the geodesic that were, in a sense, added. We go from one approximation to the next. So, can we determine a fractal translation surface? Well, the snowflake translation surface is probably not going to be something that is intuitively constructed in an intuitive way. Self-submerged Spencer carpet, can we get a hold of that? A T-fractal translation surface. That shows more promise. So, as I said, the Koch snowflake translation surface is not likely to exist in an intuitive manner. The surface will have finite area, but the singularities are going to be dense. Not necessarily in the surface, but there's going to be accumulation points and no obvious way of getting through those in the sense that they constitute removable singularities in some way. Except for finitely many examples. The sequence of compatible periodic orbits does not appear to be converging to something nice. Like we saw before, that didn't seem to be going anywhere. Spencer carpet, too many singularities in all the wrong places. Translation surface with no area. A self-similar Spencer carpet, you remove all the area. A non-self-similar carpet, though, you keep some area. That might be something worth looking at. So, the T-fractal gives rise to a surface, perhaps, that has finite non-zero area, a sequence of compatible periodic orbits that converges to a well-defined path from the T-fractal billiard table, and hence it's reasonable to expect the geodesics would do the same thing. So the question is some type of infinite translation surface? Now looking at the definitions of an infinite translation surface, you need infinitely many polygons glued together, if I understand that correctly. And then there's two types of singularities that have been talked about so far on an infinite translation surface, and that's the tame singularities and the wild singularities like Anya mentioned yesterday. So the genus of these translation services is increasing without bound, and that, in a sense, for me at least, says that this is an infinite translation surface, and maybe not the way in which we've talked about this week, but in some sense. Suppose we could construct a well-defined fractal translation surface. So the conic singularities of a fractal translation surface would be described as follows. A visible conic singularity that's either movable or non-movable depending on the cone angle, and then what I'm calling an elusive conic singularity. So the points of a fractal that are elusive points in the associated translation surface, whatever that ends up being, would constitute elusive conic singularities that are either removable or non-removable. Now notice how I don't mention whether or not they have a particular cone angle. So a visible conic singularity would either be something coming from a prefractal billiard table where the conic angle and about the point in the associated translation surface was 2 pi, or it was a Cantor point, which also has a conic angle of 2 pi, but in more of a trivial way. And then a non-removable visible conic singularity is just something that was your traditional non-removable conic singularity in some approximation. But I call them visible because you can see them in some kind of approximation. If you're trying to approximate your fractal translation surface, you can go enough times out and see, okay, there's that singularity I was talking about. An elusive singularity, you can't. You can't write down, or you can't actually draw the fractal in such a way that you can see an elusive singularity. You can only see them abstractly. So a point P of the translation surface, or a fractal translation surface, would be an elusive conic singularity if, one, P is associated with an elusive point of the fractal billiard table, and for all but finitely many directions, a sequence of compatible orbits yielding a non-trivial path itself converges to a well-defined path of the fractal billiard table. We have not seen this yet for the Koch snowflake, except for finitely many examples, but yet we see this for infinitely many examples in the T-fractal. So the points of the T-fractal that constitute the elusive points in an associated translation surface, once we've constructed that in a well-defined way, should constitute removable elusive singularities. So P is a non-removable elusive singularity if it's associated with some elusive point of the fractal billiard table, and then for all but finitely many directions, a sequence of compatible orbits yielding a non-trivial path does not converge to a well-defined path of the fractal billiard table. Again, that example I gave you earlier, the sequence of orbits was not doing anything nice. It did not seem to be quickly converging to something. So that point, P, in the surface that's associated with that elusive point in the billiard table would be a non-removable conic singularity of that fractal table because of what's happening on the sequence of billiard tables approximating the fractal billiard table and like that. So here's a Cantor point. That's a corner, and that's, yes, also a corner, but this is something with a conic angle of 2 pi. So this would be a visible conic singularity, and this would be also a visible conic singularity as well as that, but this would be a non-removable visible singularity, and this would be a removable, as with this. But in the next approximation, we see the neighborhoods about these points are getting smaller if we're only going to encapsulate just that singularity. So it's for this reason why I don't think these are wild singularities or even tame singularities. They're not tame because so right, if one could construct a well-defined fractal translation surface, then these, no, hold on. Right, so these, I wouldn't say these are wild singularities because the neighborhood, so the conic angle about them in each approximation is finite. If we construct a fractal translation surface and the conic angle about such a point in some sense remains finite, then it wouldn't be a wild singularity. If it's a tame singularity, well then that means that the neighborhood about the point shouldn't shrink. It may be finite, it's going to be infinite, but the problem is that the neighborhood about these singularities are getting smaller and smaller. So the question that I've been asking over the last several months, not necessarily of anybody, but also at the same time of Gabby, is can her algorithm be adapted in such a way that we can construct a sequence of, or calculate of each group for an approximation that finds some pattern in that construction or that calculation of the beach group, and construct a sequence of beach groups and see if it's converging in some sense to something that would constitute a beach group. It's a very ambiguous statement, but the hope is that if I can't get a hold of a fractal translation surface explicitly, maybe I can come around some back way and say, okay, if I can construct everything that the translation surface should have, maybe that would point to what the translation surface should be. So a very far off answer, or maybe not, I don't know. This is something I do want to look at and would love any input from you guys. So presumably a fractal translation surface has the following properties. Infinite genus, compact, periodic cylinders are exactly closed geodesics. We saw before that the periodic cylinders were breaking up with each successive approximation. And elusive and visible conic singularities serve as proper notions for singularities of this fractal translation surface. Now, that's not to say that the only types of singularities that we'll see are these which I define, but this seems to be a good place to start in trying to describe what a singularity of a fractal translation surface would be. So when we're working with fractals, it's sometimes helpful just to go back to a lot of the terminology and structure that fractal geometry provides. Self-similar tilings. This might be a way of getting a hold of a fractal translation surface. We can tile each approximation of the Koch snowflake translation surface by hexagons in a way that is very fractal-like and starts to point to maybe a self-similar tiling in some way. And in fact, in the Sierpinski carpet, that surface, we can get a hold of a self-similar tiling. So work done by my advisor and one of my thesis brothers, and also Stephen Winter, who's at Koch School University, or KIT, the Koch School Institute of Technology. Might be useful, in particular this notion of fractal sprays, which is a glorified Cantor set in 2D. What about self-similar groups? Work on self-similar groups done by Nakashevich may be useful. I say this because if I'm looking at a beach group, maybe this particular group that we get, taking the inverse limit or direct limit of each group is self-similar, and maybe that helps us in some way. But again, this is all structure that I'm trying to build up so that I can perhaps have enough things to point to what the translation surface should be instead of trying to get at it explicitly. And maybe a symbolic approach, work done by Robin Miller and John Smiley, symbolic dynamics, as well as I'm sure a number of others, might be useful in providing insight on what this translation surface should be. And then also, as I mentioned before, the work of Gabriella Fusen, construct a beach group from a sequence of beach groups and work backwards. So thank you.
So we'll ask many questions, so I should like to ask, are there answers?
Answers are good.
Maybe some questions.
Sure.
Maybe you mentioned this is what you meant when you said symbolic dynamics, but have you tried to consider what are the IITs that arise if you take a segment and you do the IIT, you could have convergence of the IIT.
Mm-hmm. That's also something I want to look at, and Chris Johnson and I are probably going to talk about that later. Yeah, no, that's especially with the T-fractal. I think that's actually going to be a very useful approach to understanding what even constitutes dense orbits of the T-fractal. Yeah. Yeah.
I remember one of your slides that you said was not a nice picture. Can you go back to that one?
Sure.
I had to go out, but I missed one part, but I remember that one. Can you go back there? Yeah, there. So there is a sequence, we see a sequence of periodic of cylinders, right?
This is a sequence of closed geodesics.
Closed geodesics, and as you take more and more geodesics, you have more of this picture, and you said it's a useless image. I disagree. Probably you have the notion of a lamination in this case, and I don't know if the limit object in this case could be something.
Laminations?
Yeah, like Ara's talk. I pity that Ara is not here, but maybe the limit object is a closed subset of these guys, and the natural object to see as the limit is a lamination.
Okay.
But
Is
this is just I'm not
Is this
making
picture
an.
be more helpful?
Yeah, I can
in
tell more.
understanding what you're saying?
Yeah.
Okay.
But it's just a gut feeling I have. Not
Yeah, I would love to talk about that afterwards.
Okay.
Vocabulary is something I lack
Me
with
too.
regards to the subject. I mean, I, in a sense, grew up academically in faculty geometry, and my advisor gave me this problem and said, hey, go have fun. So I did, I wrote a thesis, and then I realized I don't know 90% of the stuff that I should.
Okay.
So
Okay.
please, I
Okay.
would love to talk about that.
Okay.
Thank you. And being recorded, so perhaps I should watch exactly what I say about it.
So on the Koch snowflake
Sure.
billiard, so most of your, I think all of your examples that you've given of trajectories have had rational slopes, which are of course well understood on these triangle tile surfaces.
Sure.
But if you pick an irrational slope, you get something ergodic.
Yes.
Do you have some results on what kinds of limit trajectories you get in an irrational direction?
Well, we do get a sequence of orbits where each orbit is dense in its respective approximation. We don't know if that really converges to anything, or if we can even begin to talk about an ergodic flow, because we don't really have a notion of a billiard map yet. But I'm going to be visiting Howard Mazer in Chicago in the fall to talk about exactly that. Thank you. Yeah, if you have any suggestions on that, I would love to hear it.
I'm starting with this picture, so if you in some sense rescale the whole thing and in each step, making times 3, don't you really get the dimension?
So if you do a blow up instead of a scaling down.
Yeah.
Yeah, you probably do start to get something that is extremely reminiscent of the wind streak billiard.
And
But not maybe the actual fractal though, because the problem with the fractal is that no matter how much you scale up or down, you get exactly the same thing you started with. Just, you have an infinite amount of detail in this picture. So you can't scale up to the point where you have something of finite length and some scale, some finite scale. There's an infinite amount of detail in the fractal.
Okay, example again.